So welcome to today's deep dive. We are looking at a really fascinating set of handwritten lab notes today that describe what honestly sounds like a physical impossibility.
Yeah, it really does read like science fiction at first glance.
Right, because we are talking about materials that are surviving internal pressures that by all conventional logic should just shatter them completely.
Completely. And we're going to get into the physics of thin film growth today. And this is all based on raw data from a material scientist's actual laboratory notebook.
And when we say raw for you listening, we really mean it. These aren't polished academic conclusions that have been peer-reviewed a dozen times.
No, not at all. They are real-time observations of a totally chaotic process. The scientist here is actively grappling with carbon nitride films and trying to understand why these microscopic layers, and we're talking nanometers thick here, behave just completely differently than the bulk material.
It's the classic thin film paradox,
Yeah.
right? You have these stresses that would absolutely rip a normal bulk material apart.
Oh, yeah, tear it to shreds.
But the film just remains stable. And the notes actually open with this staggering statistic right off the bat regarding internal stress. The author just casually records values between 10 to the ninth and 10 to the 10th dynes per square centimeter.
Which is a number that is hard to even visualize. I mean, to put that in perspective for you, 10 to the 10th dynes per square centimeter is effectively the yield strength of high-grade bulk steel.
Wow.
Yeah, it is a massive amount of force.
So we have a film living in this permanent state of near failure.
Right.
Like if you applied that much external force to a steel bridge, it would buckle.
It would buckle and collapse, but here, the material is just sitting there on the lab bench.
Right, just sitting there. Why doesn't it explode?
Well, that's the key. This is intrinsic stress. It's not applied from the outside like a weight pushing down on it. It is built directly into the atomic architecture as the film grows.
Okay, so it's baked in.
Exactly.
Yeah.
The atoms are being forced into positions they really do not want to be in. It's creating this tightly coiled spring at the molecular level.
And the notes make it very clear that this isn't just some weird mechanical curiosity to write down and ignore. This stress fundamentally alters what the material actually is.
Right. It changes its entire identity.
There is a list right here in the margins connecting that stress to electron transport and magnetic properties and even superconducting properties.
And that is the critical link in all of this. When you have that much internal pressure, that 10 to the 10th dynes, you are physically squeezing the atomic lattice. You are actively changing the distance between the atoms themselves.
Which would obviously change the electronic band structure.
Precisely. I mean, think of electron transport like a highway system.
Okay.
In a normal, relaxed material, the lanes are a standard width. Traffic flows how you expect. But under this immense intrinsic stress, you are basically merging lanes or just shutting them down entirely.
Because the atoms are literally closer together.
Right. So in some materials, this squeeze increases electrical resistance. But in others, like certain superconductors, that lattice compression can actually enhance the phonon interactions that you need for zero resistance.
That is wild.
It is. You are basically turning mechanical stress into an electronic superpower.
The notes also mention optical properties. I assume that's the exact same mechanism at play, like you change the density of the material, so you change the refractive index.
You change how light interacts with the electrons. Yes.
So this scientist isn't just sitting there worrying about whether the film is going to peel off the substrate.
But they're looking at the bigger picture.
They are noting that the stress is actually a tuning knob. You can tune the physics of the device by controlling the stress.
Which leads us perfectly to the second big paradox in these notes. We have a material under this immense crushing stress, and yet the author claims these thin films exhibit, quote, large tensile strength.
It seems totally contradictory, doesn't it? Usually if something is highly stressed, it's incredibly fragile and weak.
Like a stretched rubber band that's about to snap. Exactly.
But here the strength is attributed to something specific. I'm looking at the quote in the notes. It says, high density of defects frozen in during the atomistic deposition process.
Frozen in is such a poetic phrase for a physics notebook, but physically, it describes non-equilibrium thermodynamics perfectly.
Break that down for us. What does frozen in mean here?
So when you deposit a thin film, you are essentially blasting high-energy atoms onto a relatively cold surface.
Right.
They land, and before they can wiggle around to find their perfect lowest energy spot in the crystal lattice, the next atom just lands right on top of them.
Like flash freezing them in place.
Exactly. So they are structurally locked in.
Trapped in a high energy state.
Yes. And because of that chaotic rapid-fire process, the notes estimate a dislocation density of 10 to the 10th to 10 to the 12th per square centimeter.
That is just a staggering number of defects. I mean, in the semiconductor world, we usually spend billions of dollars trying to eliminate defects. We want perfect silicon crystals.
Oh, absolutely. Defect is a dirty word usually.
But here the notes seem to imply that the defects are the actual source of the strength.
They are. Because in the bulk material world, a dislocation is a weakness, specifically because it can move.
Okay.
If you bend a metal paperclip back and forth, you are actually moving dislocations through the metal until they pile up and it snaps.
Right. I've done that.
But imagine a traffic jam. If you have just 5 cars on a highway, they can move fast. If one crashes, it's a mess, it disrupts things.
Sure.
But if you have completely gridlocked bumper-to-bumper traffic, which is what, 10 to the 12th defects per square centimeter, basically represents nothing can move at all.
Ah, I see. The defects are pinning each other in place.
Exactly. They block each other. The notes explicitly mention restrained dislocation growth as a key factor. Even if a defect wants to slip and cause a mechanical failure, it is surrounded by a trillion other defects completely blocking its path.
So the material is incredibly strong, specifically because it is broken everywhere all at once.
In a manner of speaking, yes. It's a gridlock of flaws. And the notes also cite the absence of dislocation sources as the second main reason for the strength.
What does that mean exactly, dislocation sources?
Well, in a large bulk crystal, you have these microscopic structures called Frank Reed sources that generate brand new dislocations when the material is stressed.
Like a defect factory.
Right, a factory for flaws. But in a thin film, you often literally just don't have enough physical volume for those sources to operate.
It's just too thin to fail in the traditional way.
Right. The physical geometry prevents it. And the notes also point out that point defects strongly contribute to this locking mechanism.
Point defects being like, what, just a single atom out of place?
Yeah, typically vacancies where an atom is missing, or interstitial atoms, which are atoms jammed into gaps where they shouldn't be. They act like little anchors in the lattice.
Now, there is a line here about annealing, which I found really counterintuitive. Because normally, you anneal a metal by heating it up to relax it and clear out the lattice, right?
That's the standard metallurgical approach, yes.
But the scientist wrote high degree of point defects due to annealing. Why would heating it up cause more locking?
It really depends on the specific material system. Sometimes annealing provides just enough thermal energy for those random point defects to cluster together or for tiny precipitates to form.
So they gang up.
Basically. And those clusters act as even stronger anchors, which further locks the structure before the whole thing has a chance to fully relax. The scientist is basically noting that the thermal history of the film is just as important as the actual deposition process.
Which is a perfect segue into the recipe section of these notes, because the experimental setup gives us a huge clue about what they were actually trying to achieve in the lab.
Right. The methodology is always revealing.
They are specifically growing carbon nitride films, CN films.
Which is a notoriously difficult material to synthesize correctly, by the way.
Really? Why is that?
The nitrogen just doesn't want to incorporate into the carbon lattice easily. It tends to form gas and escape.
Well, that makes the rest of this even more interesting. So they are depositing this tough carbon nitride onto specific substrates. The notes list SS304, which is standard stainless steel, then Cy100 silicon wafers, and also just regular glass.
A good variety of bases to test on.
And for the actual deposition mode, they explicitly list both RF and DC modes.
Now that is a really key technical detail right there.
The RF versus DC.
Yeah. DC, or direct current sputtering, is like a constant fire hose of ions. It is great for highly conductive metals like that stainless steel substrate they use.
Okay, but carbon nitride isn't necessarily conductive, right?
Exactly. It can be highly insulating. And if you hit an electrical insulator with a continuous DC current, a static charge builds up on the surface of the target.
Oh, like rubbing a balloon on your hair.
Just like that, but with way more energy.
Right.
And eventually that built-up charge discharges all at once, creating arcs inside the vacuum chamber. Literally miniature lightning bolts.
And I imagine lightning strikes are bad for a microscopic thin film.
They will completely ruin the film. Pock marks, uneven growth, you name it.
So that's why they switched to RF radio frequency.
Yes, RF alternates the electrical potential millions of times a second. So it naturally discharges that surface buildup before an arc can form.
So the fact that they are explicitly toggling between RF and DC in the notes suggests they are actively experimenting with the conductivity of the film itself.
That, or they're trying to bombard the growing surface with very different ion energy levels to intentionally control that frozen structure we were talking about earlier.
And you can actually see that control playing out in this logical chain written in the margin. The scientist basically maps out a cascade of variables.
What does the chain say?
It reads thickness is a function of deposition rate, and then deposition rate is a function of deposition temperature.
It's a literal cascade. Temperature is the master variable running the whole show.
But here is the specific finding related to temperature that really caught my eye. The notes say nitrogen percentage was higher in the films for higher deposition temperatures.
No, that is fascinating and highly counterintuitive.
Right, because you'd think volatile elements like nitrogen would just boil off or escape as a gas at higher temperatures.
Exactly. You'd expect the nitrogen content to drop as things get hotter.
So why does it go up in these carbon nitride films?
It almost certainly comes down to chemical kinetics versus thermodynamics. Forming solid carbon nitride requires breaking some very strong atomic bonds first.
So the heat helps break the bonds.
Yes. The higher temperature provides the necessary activation energy for the nitrogen atoms to actually chemically react and bond with the carbon.
Instead of just bouncing off.
Right. At low temperatures, they might just sit on the surface momentarily, what we call physisorption, and then float away. But with enough heat, you move to chemisorption, real permanent chemical bonds. So heat literally makes the chemistry stick.
That makes a lot of sense. The notes also mention how temperature affects the surface quality. It says at higher temperature, roughness was less, so it's smoother.
Which brings us right back to the concept of surface mobility.
The skating atoms.
Exactly. When an atom lands on a very hot substrate, it has excess thermal energy. So it doesn't just freeze immediately. It can skate around on the surface like a puck on freshly Zambonied ice.
Looking for a place to settle.
Right. It finds a valley or a low-energy spot and settles in. That natural movement smooths out the entire film layer by layer.
Whereas on a cold surface,
It just hits and sticks. And hit and stick growth naturally creates tiny microscopic peaks and valleys, which is the literal definition of surface roughness.
So the scientists here essentially found this incredible sweet spot. High temperature gives you better chemistry, meaning more nitrogen is trapped, and it gives you better morphology, meaning a much smoother surface.
It's a win-win for the material properties.
But there is a limit. And this is the part of the laboratory notes that almost feels like a thriller movie cliffhanger. It's the 100 nanometer threshold.
Oh, yes. This is where the physics of the whole system just snaps, literally snaps.
The notes state very clearly, thickness 100 nanometers dash dislocation starts. And then right below that, importantly, it says main factor in dislocation start is thickness itself.
Right. This is a classic concept in thin films. It's known as the Matthews-Blakesley limit, or critical thickness.
How does that work? Why does thickness matter so much?
Imagine you are stretching a thin rubber sheet tightly over a wooden table. You can stretch it a little bit and it stays perfectly smooth and intact.
That's the elastic strain.
Exactly. The film is straining to perfectly match the atomic spacing of the substrate beneath it.
But if you keep stretching it, or in this case, if the film keeps getting thicker and thicker, while under that 10 to the 10th dynes of stress,
Eventually, the mechanical energy required to keep stretching that lattice becomes higher than the energy required to simply rip the material.
it reaches a breaking point.
At exactly 100 nanometers for the specific carbon nitride system, the accumulated intrinsic stress just becomes too much. The material essentially decides that it is energetically cheaper to break than to keep stretching.
So it nucleates a dislocation.
Yes, it creates a structural fault, a tear in the lattice, just to relieve that massive pressure.
And the notes actually calculate the specific stress required for this nucleation to happen. It's written here as stress of G over 25 for nucleation.
Ah, okay. G over 25.
Now, G is the shear modulus, right?
Yeah.
Basically a measure of the stiffness of the material itself.
Correct. And to give you some context, theoretical maximum strength for a perfect crystal is usually estimated somewhere between G over 10 and G over 30.
So G over 25 means
It means this thin film is being pushed to its absolute theoretical limits of physics before it finally yields and creates that first dislocation. It is holding on to an insane amount of energy.
it's confirming that these films are sustaining loads that are basically impossible to achieve in a bulk piece of metal or crystal.
Absolutely impossible.
There's actually another really interesting threshold mentioned here, and it's distinct from the 100 nanometer film thickness. This one talks about the size of the individual crystal grains within the film.
What's the note say?
It says grain size. If less than 100 angstroms will affect film thickness, due to surface tension contributions.
Oh man, this is a really deep dive into nanoscale thermodynamics now.
Right, because 100 angstroms is tiny. That's what, 10 nanometers?
Exactly, 10 nanometers. When a crystalline grain is that unimaginably small, a massive percentage of its total atoms are located purely on its surface rather than safely inside the bulk of the grain.
And why does that matter? Why do surface atoms act differently?
Well, think about a drop of water in space or falling from a faucet.
It forms a sphere.
Right. It's spherical because the surface tension of the water is actively squeezing it into the most compact shape possible.
Okay, I'm with you.
Believe it or not, the exact same physical thing happens to these tiny, solid, crystalline grains.
Solid rock can have surface tension.
Yes, at the nanoscale. The surface tension creates what's called a Laplace pressure that physically compresses the solid grain inwards.
So the notes are saying that this nanoscale squeezing effect from the grain's own surface is actually strong enough to fight back against the growth of the overall film.
Exactly. The geometry of the grain itself creates a literal back pressure. It alters the fundamental thermodynamics of how the atoms attach and grow.
It really is a powerful reminder that when things get down to this 10 nanometer scale, you just cannot ignore the skin of the material anymore.
Not at all. The surface effects literally become the dominant bulk effects.
Finally, as we look at the last section of these notes, the scientist identifies the actual culprits. Once we pass that critical 100 nanometer threshold, and the material finally does start to break, where exactly do those microscopic breaks originate?
They usually start at the weak links. What did they list?
The list is just three things: GBs, twin boundaries, and PPTs.
Yep, the usual suspects in material failure. GBs stands for grain boundaries. That is simply the chaotic, highly mismatched interface where two differently oriented crystal grains happen to meet.
Like two mismatched puzzle pieces being shoved together.
Perfect analogy. It's a naturally weak and chaotic zone.
And what about twin boundaries?
Now, a twin boundary is actually highly ordered. Imagine looking at a crystal lattice in a mirror.
Okay.
The atomic structure reflects perfectly across a specific plane, so it's not a messy gap like a grain boundary, but it is a sudden, sharp change in the physical orientation of the crystal.
And that causes problems.
While they act like solid walls, they are great because they stop existing dislocations from moving, which adds to that immense strength we discussed.
Right, the traffic jam.
But because they are such hard boundaries, they can also act as intense stress concentrators. So when the pressure gets too high, that is exactly where a brand new defect will snap into existence.
Got it. And the last one? PPTs. That's precipitates, right?
Yes, precipitates. These are basically tiny microscopic islands of a completely different chemical phase or just clumps of impurities.
So in a carbon nitride film, a precipitate might be what?
It could be a little isolated cluster of purely bonded carbon, like a tiny speck of diamond or graphite forming where it shouldn't.
And that little island stresses out the surrounding lattice because it doesn't fit right.
Exactly. It's a pebble in your shoe.
So these three things, the grain boundaries, the twins, and the precipitates, these are the structural weak points where the pent-up massive energy of that 10 to the 10th dynes finally finds a release valve.
Yes. Or if you want to look at it from a structural engineer's perspective, these are the critical anchor points that manage to hold the entire highly stressed system together right up until that final critical thickness limit is reached.
It really fundamentally changes how you look at the concept of structural failure. Because in everyday life, we usually think of stress and tension as bad things to avoid at all costs.
Absolutely.
But reading through these raw laboratory notes, it really seems like stress is the actual engine of the material.
It is the engine. In the realm of thin film physics, stress is simply a form of stored potential energy. You are actively banking massive amounts of energy directly into the atomic structure to get the properties you want.
Which is just incredible. So for you listening, let's recap this journey we've been on through these notes. We started by looking at massive internal pressures, right? 10 to the 10th dynes per square centimeter.
Yield strength of steel trapped in a nanometer layer.
Right. And then we explored how that frozen defect structure creates this paradoxical, immense tensile strength instead of making it weak.
The bumper-to-bumper traffic jam of atoms.
Exactly. Then we dug into the specific temperature recipes required to trap volatile nitrogen and smooth out the surface roughness.
Using thermal energy to control the chemistry and the mobility.
And finally, we hit that critical 100 nanometer limit where the material is basically forced by the laws of thermodynamics to evolve and nucleate dislocations to survive.
It really paints a comprehensive picture, doesn't it? It's a portrait of a material violently fighting to exist in a high-energy state.
It really does. And it makes me think back to that one specific phrase the scientist wrote, frozen in, because essentially we are building these materials atom by atom, manually trapping chaos just to create strength.
That is the pure essence of material science right there.
And it leaves me with this thought. If we can figure out how to successfully freeze mechanical stress, 10 billion dynes of it, into a completely stable, functional electronic material, what else is possible out there?
That is the big question.
You're essentially pausing a chemical explosion in midair and then using it as a functional coating for a microchip.
Mm.
So it raises this provocative question for you to mull over. What other transient, violent, high-energy states could we somehow freeze into place that nature absolutely never intended to be permanent?
And exploring those metastable states is exactly where the frontier of advanced physics is heading today.
And that is a deep dive for another day. Thank you so much for exploring these fascinating lab notes with us.
It was an absolute pleasure to be here.